Hi, this is Mr. Ward, and this is an 8.4 walkthrough just of the sort of sample problems on the beginning of it, and then I'll do one about some of the problems. So for this one, we're going to be taking some of the principles from 8.3 and just working them in reverse. There's no new theorems introduced here. It's just turn the theorems around and you can get some information about angles and something about proportionality of sides. So if in example 1, we've been given that triangles ABC and DEF are similar, and we're supposed to prove that angle A is congruent to angle D. Well, the corresponding angles of similar triangles are congruent. So A and D are corresponding, and so they're therefore congruent. Now, for example 2, we've got, again, triangle ABC and DEF are similar, and we're supposed to prove that AB is to DE as AC is to DF. Well, since they're similar, corresponding sides of similar triangles are proportional. You can think of that as AB is to AC. Okay, so you can also say that AB is to AC as DE is to DF. That's an equivalent sort of rotation of the proportion. So AB and DE are in a horizontal position, just like AC and DF are, just as AB and DE and AC and DF are in vertical positions in the proportion. The product of the means and the products of the extremes will still work out to DE times AC and AB times DF. DE times AC and AB times DF. It is the same proportion. It's just rotated. Now, in example 3 here, we've got triangle ABC is similar to DEF again. Now, we're supposed to prove that AB times DF equals AC times DE. So this is just taking that proportion one step further and saying the means, the product of the means equals the product of the extremes. So we can take the AB and the DF and the AC and the DE. So there's AB and DF and AC and DE. And we know that AB will be to DE. So AB is to DE as AC is to DF, or AB is to AC as DE is to DF. Either way, the product of the means will equal the product of the extremes, and it will produce this set of products that are equal to each other. So AB times DF, that's the product of the extremes here. Again, AB times DF, and then DE times AC, or AC times DE is the same thing. That's the product of the means. You get the same dang thing either way. Now, here's some sample problems we'll take a look at. I'm going to move my picture out of the way, and let's look at the sample problems. So we've got that BD is parallel to CE. And what that tells us is that AC and AE are both transversals. So that's very convenient. That'll help us. And we're supposed to prove that AB is to AC as BD is to CE. All right, so to do that, it's going to be useful to prove that ABD and ACE are similar triangles. So we know that ABD is congruent to angle C because those are pairs of corresponding angles. We know that ADB and angle E are congruent, also pairs of corresponding angles because of the transversals that are set up by the parallel lines. And therefore, we have angle-angle. That proves that triangle ABD is similar to triangle ACE. ABD and ACE are similar triangles by angle-angle. And then because of that, we can say that AB is to AC as BD is to CE because corresponding triangles of corresponding sides, I should say, of similar triangles are proportional. Now, number 2 is a little bit weirder, but it's a lot simpler than it looks. We've been given a parallelogram, YSTW, and we're told that SX is perpendicular to YW, so that sets up a right angle right here. We're also told that SV is perpendicular to WT, so that sets up another right angle. And we're asked to prove that Sx times YW equals SV times WT. All right, so that's a little weird. What do WT and YW have to do with anything? Well, you might remind yourself this is a parallelogram, so YW is the same as ST, which is part of this triangle. And WT is congruent to YS, which is part of this triangle, SXY. And we have resources now to prove that these triangles are similar. So we can prove that we know that Y and T are going to be congruent because they're opposite corners of, or opposite angles of a parallelogram, opposite corners, opposite vertices, and they're the angles there that are opposite and they are congruent. We also know that SXY and SVT are right angles because we were told that those were perpendicular to those sides. And so now we have angle, and we can prove that SXY and SVT are similar triangles. Then we can take the parts that are here. So SX and SV are parts of those triangles. And we can say that SX is to SV, which happens to be congruent to WT, as SV is to ST. And then you can multiply that out. Sx times st, that's the product of the extremes, equals the product of the means, sv times sy. But since st is congruent to yw and sy is congruent to wt, we can simply substitute wt for sy. So wt and sy are interchangeable because they're the same dang thing in measure, and YW can be exchanged for ST. And so we can substitute those congruent sides in for ST and SY, and we end up with SX times YW equals SV times WT. Now, the other type of problem is called the shadow problem. And so here, let's read this. So while strolling one morning to get a little sun, Judy noticed that a 20-meter flagpole cast a 25-meter shadow. And, because Judy is who Judy is, she apparently wanted to work out some things. So nearby was a telephone pole that cast a 35-meter shadow. How tall was the telephone pole? So because the sun is so very far away, the difference in the angles of these shadow setups are pretty much virtually the same. There are slight differences, but you can assume that if you're in the same neighborhood, the angles are close enough that it does not matter. Okay. So because the sun is very far away, its rays are nearly parallel. Now we're going to assume that the telephone pole and the flagpole are at right angles to the ground. That's an assumption. They are not always. I've definitely seen some bent over flagpoles and telephone poles. But for the purposes of this problem, we will assume that they are at right angles. So we want to know how tall the telephone pole is. So we just say that's X. We know the shadow is 35 meters long. We know the flagpole height is 20 meters, and the shadow here is 25 meters long. So we can assume 90 degrees and 90 degrees, and we can assume that the angle of the sun hitting here or the angle of the sun hitting the top and producing the shadow, all the angles are going to be congruent, and so these triangles will be similar. So we can simply say X is to 35 as 20 is to 25, or we could say X is to 20 as 35 is to 25. Does not matter. We will find out what X is. X will end up, so we do X to 35 as 20 to 25. We can reduce that to make our life easier and make that 4 to 5. And now X is to 35 as 4 is to 5. And so we get the products of the extremes and the products of the means. You can do the shortcut of bat and ball because that's based on this, because what you're going to do is 35 times 4 is 140, and then X times 5 is 5X. Then we'll divide the 140 by 5. And then X will be 28 meters. So the flagpole is 20 meters. The telephone pole is 28 meters. Now, These little things are always worth taking a little time on. The Royal Road, Euclid's Proposition 2 from Book 6. If a line is parallel to one side of a triangle, it divides the other two sides proportionally. And so this is one way to prove this property is use the angle-angle theorem. In Euclid's organization of the elements, which is a very famous and important book of mathematics and geometry, did not actually have the angle-angle theorem, so he used some other things. So he knew that if two triangles have congruent altitudes, then their areas are proportional to their bases. Okay, and so he noticed, that BEA and BEC have the same altitude, okay, from E. So here's an altitude from E. Okay, and similarly, EBA and EBD, so EBA and EBD also have the same altitude and the same base. Okay, so let's see. So let's see now. Can we show the following? So let me move my picture out of the way. Okay, so AB is to BC as the area of BEA is to BEC. And and that's also going to be the area of EBA as is to EBD, as AE is to ED. Okay, and I think that would be worth exploring and seeing if you can prove that. But I'm going to go ahead and stop this video and let you consider that. My next video will talk about the problems in 8.4.